Okay everyone, this video is going to be about chemical bonding. This video is a little bit longer than most of the videos because we're talking about a lot in terms of chemical bonding. So first we want to talk a little bit about what a proton and an electron is. Okay, a proton is a positively charged particle that is in the nucleus of an atom. Okay, so it has a positive charge, and as we discussed before, electrons have a negative charge. Okay, now every atom on the periodic table, as it appears, is neutral. And the reason for that is every atom on the periodic table has the same number of protons and electrons. So they have no charge. Okay? But some atoms on the periodic table, or rather most atoms on the periodic table, are looking to balance out their outer shell or their valence shell. So as we spoke about in a previous class, the valence shell is the outermost shell on the periodic table. Now, just to give you a little bit of a reference point, if you look at your book on page 35, you have a copy of your periodic table, and you'll notice that you have groups 1A to 8A. Okay, we are ignoring the transitional metals right now. We're just looking at groups 1A through 8A. So those are the groups that begin with hydrogen, okay, and then beryllium, boron, carbon, nitrogen, oxygen, okay, and then we have fluorine, and helium is at the top of the 8th group. Okay, so these are the tops of groups 1A through 8A, so you can use those elements as a reference. Now, if you looked at the periodic table in my class, you noticed that in the periods, okay, the periods are the rows across, okay, the periods show how many electron shells each atom has, each element has. So as you go down the periods, hydrogen is in the first period. Hydrogen and helium only have one shell. Lithium through neon have two shells. They're in period 2. Sodium through argon have 3 shells. They're in period 3, so on and so forth. So when you look at your periodic table, you will see that the number of shells that each atom has, or each element has, corresponds to the period it's in. Now the group that it is in, okay, the group number, again, we're only looking at 1A through 8A, corresponds to the number of electrons in the outer shell or valence shell. Okay, let me make that a little bit easier to read. Okay, in the outer shell. Okay, now the goal of every atom is to have a balanced outer shell or a stable outer shell. In other words, to max out its outer shell, or in the cases of the larger atoms, to have at least 8 electrons in the outer shell. Now, all of group 8, all of them already have a stable outer shell, so they're happy. But groups 1A through 7A, they are not really happy. They want to maximize their outer shell. So if we look, we have group 1, 2, 3, 4, 5, 6, 7. Okay? When we look at groups 1 through 7, we're looking at how many electrons they have in their outer shell and what they have to do to fill their outer shell. Now group 1 has 1 electron in its outer shell. Okay, so this is our group. It has 1 electron in its outer shell. It's going to take the path of least resistance. It's not going to gain 7 more electrons to get to 8. It's going to lose 1 electron. So because electrons are negatively charged and protons are positively charged, when it gets rid of 1 electron, for example, let's say sodium. Sodium has 11, okay? Sodium has 11 protons and 11 electrons, right? So if sodium loses 1 electron so that the shell below it, the second shell, is full, okay, it will now, minus 1 electron, it will now have 10 electrons. So since it has 10 electrons and 11 protons, that means it has 1 more positive charge than negative charge. So it will become positively charged, or 1 plus. Now this is called its oxidation number. Okay? Now group 2 has 2 electrons in its outer shell. Okay? Since it has 2 electrons in its outer shell, it's going to get rid of 2 electrons. It's easier to lose 2 than gain 6. So it will have a charge of 2 plus. Ooh, I'm getting ahead of myself. It'll have a charge of 2 plus. Group 3 will get rid of 3 electrons. It will have a charge of 3 plus. Now group 4 is a little bit different. It will be 4 plus or minus. Now in this case, it could either, for simplicity purposes, just know that the bonding is a little bit different with this group, but for simplicity purposes, we're going to say it could either gain 4 or lose 4, so it can function on this side or on this side. So we put 4 plus or minus. Okay? Group 5 already has more than half of the electrons it needs. So it is going to gain 3 electrons to have a charge of 3 minus. Now it has more negatively charged particles than positively charged particles. Group 6 is going to be 2 minus, and group 1 is going to be 1 minus. Now, an easy way to remember how the oxidation numbers move as you go along from 1 to 7, okay? 1 plus, 2 plus, 3 plus, 4 plus or minus, 3 minus, 2 minus, 1 minus. So if you notice, it follows an arc where 4 is at the top. We're climbing from the positive side and then descending from the negative side. So it is 1, 2, 3, 4, 3, 2, 1. If you look at the group numbers, again, the goal is to get to 8. It is easier to drop to get to 8. So you're going to drop 1, drop 2, or drop 3. Here, it's either gain or lose. You're going to gain 3, gain 2, or gain 1. Okay? So, once we've actually accomplished this, we're going to start practicing how chemical bonding works. So you saw me do this in class briefly, but we're going to do this here. Okay? I have a system that I developed called FROGS, and FROGS is the acronym. It's actually backwards. It allows us to determine the simplest elemental bonds that occur ionically. So it is S, G, O, R, F, or FROGS spelled backwards. And this actually, let me go ahead and move this over a little bit so I can tell you what it means. It is the chemical symbol, group number. Okay, this is the oxidation number. Let's fix that O. Okay, oxidation number, ratio, and formula. So we create this chart. So let's say I'm going to start with calcium. So let's say I want to make calcium chloride and I want to see how they bond. Well, calcium is closer to the left side of the periodic table. When we read the periodic table, we read it from left to right. And since calcium is in group 2 and chlorine is in group 7, calcium will appear first and chlorine is here. Now, as I said, calcium is in group 2 and chlorine is in group 7. Well, if we look at our chart here, elements in group 2 have an oxidation number of 2+. So we put this here. And elements in group 7 have an oxidation number of 1-. So we crisscross them and drop the sign, so the 1 is going to come over here and the 2 is going to come over here. So now we have our ratio. They will bond in a 1-to-2 ratio. So we bring our chemical formula down and we bring our ratio number down, Cl2. So the bonding ratio is Ca1Cl2. Now we do not normally put the 1, but I just wanted to show you how we bring the ratio down. We do not use the 1 in chemical formulas. If the element symbol is represented in the formula, then it is understood that that element is present. If there is no number with it, no subscript, then that means there is only one of that element. So the chemical formula here is CaCl2, calcium chloride. Okay? Now, let's go ahead and do another one. So let's say I'm looking at sodium and chlorine. Okay? And you can abbreviate this as long as you know what goes where. Okay, so the group number for sodium is 1 and the group number for chlorine is 7. Sodium therefore has a charge of an oxidation number of 1+. Chlorine's oxidation number is 1-. So it crisscrosses to form a ratio of 1-to-1. So it is NaCl, which, by the way, is the chemical formula for table salt. So let's do one more. There's one I would like to kind of go over. If we look at groups 2 and group 6, they actually bond at a 1-to-1 ratio as well, but their oxidation numbers are different. So let's go ahead and look at magnesium and let's say sulfur. So magnesium sulfide. So magnesium is in group 2 and sulfur is in group 6. This has an oxidation number of 2+ and 2-. So when we crisscross them, it is 2-to-2. Now in this case, you would have Mg2S2. However, they bond at a 1-to-1 ratio because they are in group 2 and group 6. You would actually, in this case, reduce it to its smallest factor, which is Mgs. Now, I doubt you'll be seeing something like that on the test, but I just wanted to introduce you to that. In this case, you want to reduce your subscripts because in this case, they do bond at a 1-to-1 ratio. Okay, it would be the same thing for magnesium oxide. So you will be seeing some examples of this for us to kind of go through in class tomorrow, and we'll spend the first few minutes reviewing how to do these in class. But I hope this was a little bit of a help and that you understand oxidation states a little bit better, as well as how to use FROGS to determine the chemical formula of a simple ionic compound.